Welcome to the deep dive. It's pretty amazing what large language models can do these days, isn't it? These transformer models. They handle some incredible tasks, especially with really long texts.
Absolutely. Things like summarizing huge documents, answering questions that need info from dozens of pages apart, even analyzing code bases. It feels almost magical sometimes.
It really does.
Yeah.
And that power, it mostly comes down to the self-attention mechanism, right? That's what lets the model figure out how important every bit of the text is to every other bit, even across huge distances.
Exactly. It's incredibly powerful for understanding context and dependencies.
Yeah. But there's a pretty big catch one researchers are really wrestling with. When the text gets super long, tens, maybe hundreds of thousands of tokens, these models, even the big ones, they start to, well, hit a wall.
They get incredibly slow, and the computational cost just skyrockets.
Right. And the paper we're digging into today really zeroes in on this. They call it the curse of high dimensionality,
Yeah.
but specifically in the context of these transformers.
That's the term they use. And it's not just about more data making things harder. It's about a fundamental inefficiency in how that standard attention mechanism scales up.
Right.
The paper makes this really critical point, quoting here. While attention weights are often sparse, meaning many tokens contribute minimally to predictions, all tokens still consume equal computational resources.
That phrase, equal computational resources, for tokens that contribute minimally, that really hits home. That sounds like the root of the problem.
It's the core inefficiency they're tackling.
So our source material for this deep dive is this fascinating research paper, Curse of High Dimensionality Issue in Transformer for Long Context Modeling. And we've also got some helpful study guides and briefings alongside it.
And importantly, this paper isn't just pointing at the problem. Its whole mission is to propose and then rigorously test a new academically sound solution to tackle that exact redundancy issue, making these long context models genuinely practical at scale.
Okay, so your mission, listening in, is to cut through the jargon with us. We're going to unpack the paper, really understand the academic thinking behind it, the theories, the proofs, and then dive into the actual innovative tech they built. It's called Dynamic Group Attention, or DGA.
Sounds good. Let's peel back those layers.
All right, so to really get this curse, we need to understand the redundancy problem first. Maybe a quick refresher on self-attention.
Sure. So at its heart, self-attention involves calculating these weights. The paper uses alpha j for every token j relative to every other token I. These weights basically quantify how much token j matters for understanding or representing token I.
So wait, every single word or token is constantly checking its relationship with every other word in the entire document, however long it is.
That's the standard mechanism, yes.
Yeah.
And that leads directly to one of the key academic insights in the paper. It's formalized in their Theorem 1 and shown really clearly in Figure 2. It's this idea of attention sparsity.
Sparsity, meaning not dense, spread out.
Exactly. The theory actually proves that in these really long sequences, the vast majority of those attention weights are tiny, close to zero. Most tokens just aren't that important for predicting the next token or influencing the representation of most other tokens.
Okay, so it's mathematically proven that there's a lot of, well, dead weight in the calculation.
You could put it that way. Theorem 1 shows mathematically how the probability of this sparsity occurring, they call it pace sparse under, increases quite dramatically as the context length L gets bigger. It's not just a hunch, it's a derived property.
Right.
And then Figure 2a, 2b, 2c back this up with real-world data showing the sparsity pattern across different models, different data sets. You literally see these huge areas of very low attention weights.
Okay, so we have the theory, we have the data showing most tokens aren't doing much heavy lifting in the attention calculation. But the inefficiency, where does that actually bite?
The inefficiency, that's the crux of the curse. It comes because even though the final attention weights might be sparse, the process of calculating them, it still treats every single token pair equally.
Okay.
You're doing all those quadratic operations, OL squared complexity to figure out the weights, and then you're mixing the token representations based on them. You do the full computational work regardless of whether a weight ends up being 0.0001 or 0.1.
Maximum effort for potentially minimal payoff. That's the bottleneck for handling, say, a whole book efficiently.
Precisely. It's like running a full security check on every single fan in a huge stadium just to find the few people relevant to a specific event happening on the field.
That's a great analogy, and I guess people have tried to fix this before. What about earlier methods?
Oh, definitely. Researchers have tried various approximation techniques. The paper mentions some approaches that essentially just disregard tokens, maybe keep only the first few thousand or the most recent ones, like in methods used by streaming LLM or LM infinite.
Okay, that sounds simpler. Does it work?
Well, it cuts down computation for sure, but the paper points out a big downside. You might accidentally throw away crucial information. Think about tasks needing a deep understanding of the whole text,
Right.
like answering a complex question where the answer depends on sentences scattered far apart, or writing a summary that covers points from the beginning, middle, and end.
Right, you might literally toss out the one paragraph you needed.
Exactly. So the academic challenge they set themselves was, how do we cut way down on the redundant computation without losing that essential information, without breaking the important connections between key tokens wherever they happen to be?
Okay, so they need a smarter approach, one that can tell the difference between the computational gold and the dross, so to speak.
Yeah.
How do they rethink the theory? This sounds like where the core innovation starts.
Yes, this is a really neat theoretical shift they make. Instead of sticking purely to the standard view, predicting the next token based on all the history,
The usual probabilistic language modeling way.
right, they reframe the problem using the lens of supervised learning.
Supervised learning, like training image classifiers. How does that fit with generating text?
It's more of an analytical tool here. As they lay out, particularly around equation 2, they view the task as predicting some target yo, maybe the next token, maybe something else based on its context, which they call CIY.
Okay.
Now, why is this reformulation innovative? Because it provides formal mathematical way to actually distinguish between what they call relevant tokens and irrelevant tokens within that context. You see this in equation 4.
Ah, so it lets them define precisely what is signal and what is noise or redundancy for a given prediction task.
Exactly. 6-irs is the small set of tokens really crucial for predicting why, and 6-irs is the majority that are, well, mostly redundant for that specific prediction. This framing gives them a rigorous way to analyze the redundancy we were just talking about.
So it's an analytical perspective, not necessarily changing how the model trains day to day, but giving them a mathematical handle on the problem.
Spot on. And having that handle allows them to simplify the analysis of finding the best attention weights. They formulate it as a linear coding problem, which you see in problem 1 basically, finding the optimal way to combine the value vectors using those weights.
Okay, so this supervised learning viewpoint clarifies the relevant and irrelevant split, which then simplifies the maths, and that leads them to the idea of
Grouping. This is the next key theoretical innovation, the group coding strategy, laid out in problem 2. It flows directly from that analysis. If you've identified a large chunk of tokens as largely irrelevant, why keep processing each one individually?
Right.
The theory suggests putting them into groups. Instead of each token A getting its own weight as J, tokens in a group share a common weight, alpha bar J.
So like finding the average importance for a whole bunch of less important tokens at once.
That's the core idea. And this theoretical grouping strategy offers 2 huge advantages, mathematically proven in Theorem 2 and Theorem 3. These are really central academic contributions here.
Okay, what are they?
First, Theorem 2 proves improved robustness to noise. Basically, by averaging the contributions or representations of several tokens within a group, you smooth out random variations noise in the data or the model's internal state. The math shows the variance of weight changes drops significantly, proportional to 1 divided by m squared, where m is the group size.
Wow, 1 over m squared.
Ah.
That's a big reduction if the groups are reasonably large. It sounds like it makes learning more stable.
Exactly. And figure 3b shows this empirically. DGA is much more stable under noise compared to standard attention.
Okay, robustness was the second big theoretical win.
Theorem 3 proves accelerated optimization. Grouping tokens drastically cuts down the number of variables the optimizer needs to handle during training. It also improves something called the condition number of the mathematical problem being solved.
Condition number, like how tricky the optimization landscape is.
Yeah, a better condition number means the path to the best solution is smoother, less bumpy. So training converges faster and more reliably. And again, they show this empirically in figures 3a and 4 DGA reaches lower error levels faster during training.
Okay, this is making sense. The theory identifies the sparsity problem. The supervised view helps define it mathematically. And the grouping theory proves it can make things more robust and faster to train. That's a solid foundation. So how do they turn this theory into something that actually runs? the dynamic group attention mechanism itself.
Precisely. DGA is the practical implementation of that group coding idea, but done dynamically. Figure 1 gives a nice overview, and algorithm 1 details the steps. The core logic is figure out on the fly which tokens are focal, the important ones, and which are non-focal and can be grouped together.
And how does it decide? What makes a token focal?
It calculates an importance score for each token, usually based on things like how much attention it has received recently. Equations 16 and 17 detail one way to do this quickly. This score then drives the token categorization. The sequence gets split dynamically into 2 sets. First, the focal tokens. This is a small subset identified as important by their scores. These guys get the standard treatment processed individually, full attention calculation. Their unique information is preserved.
Star players.
Right. Then you have the non-focal tokens. These are the ones with scores below a certain threshold, the less critical ones for the current context. These are the tokens that get grouped. Their key value pairs, VNO, are essentially averaged or aggregated together, equations 14-15, to form a single representative KV pair for the whole group.
And that's where the computational saving comes in. Processing one group representation instead of dozens or hundreds of individual tokens.
Exactly. That's the main speed up.
So focus on the stars, treat the rest of the team as a unit. Makes sense. You mentioned something specific for autoregressive models earlier.
Ah, yes, the complementary KV pairs, BSLE, VCA. This is a clever bit of engineering. See, when an LLM generates text token by token autoregressively, a token can only look back at previous tokens. Now, imagine some important context happens later in the sequence, and those tokens get grouped together. A token being generated earlier might not be able to see that aggregated group information through the standard attention mechanism because the group is formed from tokens in the future relative to it.
Okay, I see the problem.
So these complementary pairs, BCFIA, are added specifically to ensure that all tokens, no matter where they are relative to the dynamically formed groups, can still access the essential information from those aggregated groups. The paper's own experiments, the ablation studies, found these were actually critical for context modeling performance, dropped noticeably if they were removed, even though they add a small bit of latency.
So a necessary addition to make the theory work properly in practice for generation tasks. Very interesting. And the payoff. What does all this dynamic grouping actually mean for computational complexity?
This is where the academic innovation really translates to practical gains. Vanilla attention, as we said, is roughly OL squared for training, OL per token for inference. DGA changes that. For training, it becomes roughly OL squared divided by M, where M is the group size.
Okay, faster training. What about inference, which is often critical for deployment?
For inference, the complexity becomes roughly OR plus LRM plus M, where R is the number of focal tokens. Essentially, you process the R focal tokens individually, process the aggregated groups, which is LRM groups, and maybe some overhead related to the number of groups M. This is much better than OL when L is large and R is small.
That looks like a huge potential speed up on paper, especially for really long sequences where L is massive and most tokens aren't focal. Did the experiments bear this out?
They really did. They ran extensive tests using standard setups like the long bench E benchmark. They measured speed using intertoken latency, ITL basically. How fast can it generate the next token?
Lower is better.
Exactly. And they measured accuracy using things like exact match EM score on question answering. They put DGA into models like LMA27B and compared it against other methods like streaming, LLM, and minference on big data sets.
And the results, what did the numbers show?
The efficiency numbers in tables 1 and 3 were pretty striking. They confirmed the theoretical gains. At a 16,000 token context length, DGA LLM was generating tokens 3.28 times faster than minference and 2.72 times faster than streaming LLM.
Wow, that's a significant speed up.
But what's maybe even more important is that DGA's ITL, its speed, stayed pretty stable even as they pushed the context length much further out. The baseline methods tended to slow down more dramatically as the context grew. DGA showed much better scaling.
So it's not just faster, it stays fast as the text gets longer.
Yeah.
That's crucial for actually using these things on massive documents.
Okay, but speed is only half the story. Did it sacrifice accuracy? Could it still understand the long context? That's the key question, right? And the performance results in tables 1 and 2 showed that, crucially, No, it didn't significantly sacrifice performance. The EM scores, for instance, were competitive with, or sometimes better than, the baselines across different context lengths.
Okay.
Importantly, DGA didn't show a major drop-off in accuracy at those really long contexts where some other methods might start to struggle because they're approximating too much or discarding information. So they managed to get that big computational speed up without really hurting the model's ability to understand and reason over the full context.
They managed to crack the code, speed and accuracy for long contexts.
Mhm.
Did they run tests to kind of pick apart why it works so well, like tuning the knobs?
Yep. They did ablation studies, detailed in tables 4 through 7 in the supplementary info. They played around with parameters like the group size M and the importance threshold to see how they affected the balance between speed and accuracy, finding that sweet spot. And those studies also empirically confirmed how important those complementary KV pairs VC were. Removing them definitely hurt performance on the generation tasks, backing up their design choice.
Okay, so it's a really well-rounded piece of work. Starts with a deep academic dive into the root cause, builds a solid theory, engineers a clever dynamic mechanism, and then proves it works with strong empirical results, speed, and accuracy.
Exactly. It covers all the bases. And they finish up by looking towards future directions. They suggest that the core idea behind DGA, dynamically figuring out what's important and grouping the rest, isn't necessarily limited to text.
Ah, interesting. Where else could it apply?
They mention things like video processing. Maybe you could group frames that are relatively static or unchanging. Or audio processing, perhaps prioritize key speech segments and efficiently handle silence or background noise. The principle seems quite general.
That makes a lot of sense. Redundancy isn't unique to language data.
Not at all.
Yeah.
So the academic contribution potentially has broader implications.
All right, so let's just quickly recap. We started with this big challenge, the curse of high dimensionality in long context transformers. Basically, standard attention gets bogged down, processing every single token equally, even when most aren't contributing much.
Right, and the paper's response was multifaceted. First, that academic reformulation using a supervised learning lens to clearly define and analyze the redundancy. Second, the group coding theory, mathematically proving that grouping less relevant tokens improves robustness and speeds up optimization.
And third, the dynamic group attention mechanism itself. The practical implementation that dynamically sorts tokens into focal and non-focal, aggregates the non-focal ones, and crucially adds those complementary pairs for generation tasks.
Leading to the final result. A system that demonstrably achieves significant computational savings, much faster inference, lower latency, without losing the ability to understand complex long texts accurately. It's a really smart way to handle that information overload internally.
Yeah, very elegant solution to managing that complexity. And it leaves you with a pretty provocative thought, doesn't it? If this fundamental problem, the curse of dimensionality, the issue of redundancy in huge data sets, can be tackled so effectively in language models using dynamic grouping, where else could this apply? What other fields are wrestling with massive sequential data where maybe only a fraction of it is truly focal at any given moment? Think about genomics, financial data streams, climate modeling. Could dynamically identifying and grouping information be a powerful tool there too?
It certainly opens up interesting possibilities for how we approach large-scale data processing across many domains.
Yeah.
A very transferable principle.
Absolutely. Lots to chew on there. Well, that's all the time we have for this deep dive. Thanks so much for walking us through it.
My pleasure. Always fascinating stuff.